in this next session of setting targets, we will discuss about energy balance, significant energy uses, energy performance indicators, energy baselines, and normalizing energy performance indicators. So moving forward, so for this topic, setting targets, these are the references in HIG FEM. Number one, track and measure energy use, standardize methods and frequency to track each energy source, establish energy baselines, identify energy intensive processes or operations, set targets for improving energy use, and set targets for reduction of greenhouse gas emissions in scope 1 and scope 2. So let's go to the energy balance. The purpose of an energy balance is to look at the energy consumption on a smaller scale now. So we are not only talking about the macro level energy balance, but now we're talking about individual energy uses. So to estimate that, for example, if we don't have measurements in one of the energy uses, what we can do is we can take nominal capacity rating. So for example, for equipment, we know that as per design capacity, as per the fabric that we're using, it should use 2 tons per hour steam when we're running a certain type of fabric. So nominal equipment rating is, for example, 2 tons per hour. Then the duty factor is is how many times it is available. So 80% time of the year it is available. Then the load factor. So is it running on full load when it is running? Is it running on partial load? So for example, the rating was 2 tons per hour, but the fabric that we have put in requires maybe 20% less steam, so that becomes a load factor in that case. And so 80% duty factor, 80% load factor, and annual operating hours are, for example, 7,000 hours. So you multiply all them together, and then it can bring our energy consumption. So this is one way of estimating as well if we don't have measurements. Obviously, another way is to do the measurements. So if we can do a spot measurement, and we know, okay, let's talk about electricity. We say a certain motor is usually running at 4 kilowatt load. But then is this motor always running, or is this motor running also varies the load? So we also need to identify that load factor. Then we also need to see if this machine runs 24 hours every day, or does this machine also have stoppages like changeovers or maintenance. So we estimate that duty factor as well. And then how many overall number of years number of hours of operation do we have in a year? And we multiply those together and we can estimate energy consumption. Another way is to put up a power data logger there, which logs data for 1 day or 2 days, and then we might have more data. So there are different means of measuring this. And then we sum up all the individual loads, and then we can compare it with the plant energy inputs. Then we need to identify significant energy uses. What are these? These are the big energy uses. So we need to define which of the uses we will call significant energy uses, and so that we can focus on those rather than focusing on everything. So sometimes, for example, lighting load is very small, but bigger load is in machines. So auditors, instead of auditing the lighting, we should spend more time on the machines, on the big motors, rather than auditing only small motors and spending time there. This way, if we have a big energy user, which we analyze in detail, and if we are even able to save small amount of energy, percentage of energy in this big user, it can have a big impact on overall factory energy consumption. So this is also important to identify the significant energy use. Example is a weaving plant. For example, this was a plant in Pakistan. As you can see that there is a 6,500 kilowatt load is going in, and this is for 62% is being used in air compressors, and 17% in the looms. So we already know that these are the main energy users: looms, air compressors, and the chillers and the heating and ventilation system, which is 11.5%. All others are only points in points, 1%, 0.7%, 0.4%. So we don't really need to focus there. And even inside these equipments, we can also see, for example, in air compressors, our bigger load is in the compressors rather than in the dryers themselves. In case of sizing, for example, we have bigger consumption in sizing as well as compressors. So here we can identify in which area we are consuming more energy and where we need to focus on. Similarly, an example of a foundry unit in Pakistan, also we did for Unido, we can see that they have electrical energy and thermal energy, and most significant inputs of energy they have are electricity from national grid, natural gas for thermal energy, and hard coke for thermal energy. And these are being used mainly in, you can see, mold preparation, melting, and post molding processes. All others are actually low consumers, so they first need to focus on melting process, then on mold preparation process, and then the post molding process. So that is how they can prioritize their efforts on energy efficiency. And then we need to set energy promise indicators. So if we know how many gigajoules or kilowatt hours we are consuming in a year, we can divide it with the kilograms of fabric or the number of garments or the meter of the fabric, whatever unit we are producing. And then we can have an indicator that is measurable against a certain production quantity. These energy promise indicators must be measurable, and we need to use them for the monitoring purposes, and they should cover all the energy sources and all the significant energy uses. So all the sources should be there. We cannot remove and move out any of the sources, but on the usage side we need to focus only on the significant uses first, and this actually helps us in demonstrating the energy performance and also compare it with the baseline values as well as target values. So for example, in this case, these furnaces are being compared with the benchmarks, global benchmarks this factory has found out. So you can see that this, in the green color, these type of furnaces are consuming more energy compared to the benchmarks. The yellow furnaces, we have the furnace number 4, which is at the benchmark value, but others are consuming more energy than the benchmark. So that is how we can compare as well. Then we talk about the baseline. So baseline is the current state. How much energy was consumed in year 2020, for example, or how much energy is being consumed against a ton of production or a kilogram of production. So these need to be based on a data which has to have a specified period and specified conditions. So for example, we could say that this baseline is from January to December 2020, or we could say that this is the baseline for summer season and this is the baseline for year 2020 winter season. So we need to specify the conditions and the specific period as well, and these baselines can be absolute. So for example, we could say that we consume 120,000 gigajoule energy per year. This is an absolute value, but we can also normalize it, that we can compare it with production quantity. So if we have more production, we have more energy consumption. If we have lower production, we have lower energy consumption. So that is how we can normalize them as well. The relevant variables we need to identify. Which are the variables that significantly impact or affect our energy performance? For example, if the environmental temperature is very low, the heating processes would consume more energy. If environmental temperature is high, the cooling processes would consume more energy. Similarly, if we have high humidity, we need more energy as well as in the cooling processes. Sometimes the energy consumption also varies because of the raw material type. So if we have cotton, for example, we need lower temperature in the stenters. If we have synthetic fibers, we need higher temperature in the stenters. So these are different significant variables that we need to identify for our baseline, and this depend on the nature of activities. We can do a simple normalization. So as you can see in point number 3, simply dividing it with the number of production quantities. This could be a simple one, or we could have a complex procedure like using a regression analysis. So what do you think? There are two companies, company A and company B, and their energy consumption, annual energy consumption is mentioned there. So company A consumes 73,843 gigajoules per year, and company B consumes 108540 gigajoules per year. What do you think? Which company is better in energy performance? And what do you think now? So in the third column now, their production is mentioned in tons per year, and then their gigajoule per ton is also mentioned. So the company A consumes 5.58 gigajoules per ton, and company B consumes 24.68 gigajoules per ton. I have some more information from you. Are they producing the same product? So yes, they are both producing yarn, but are they producing the yarn of the same quality or not? So yarn count is an indicator that indicates how many lengths of a yarn fit into 1 pound. So hank is a measure of length. So company A produces a yarn of which 8.72 hanks of length are actually weighing 1 pound, and company B produces a yarn in which 52.5 lengths of yarn weigh 1 pound. What do you think now? Can we still compare them? Tell which one is better? So what we found out when we did a baseline study, a benchmarking study based on this, was that this is company A here, and this is company B here on top. And you see this regression line slope. Both are on the same slope line, company A as well as company B. So what we found out was that company A is producing a coarse yarn. This means that the yarn is thick. So less number of lengths of this yarn weigh 1 pound. And company B is actually producing a very, very fine yarn, which means it is stretched, it is elongated. So to produce a fine yarn, they have to add processes, and they have to include more energy consumption to ensure that their yarn is stretched properly, it is fine. So it is easier to make a coarse yarn. That means a yarn with more weight than a lightweight yarn. So we found out that actually yarn count, or the lengths per pound, is actually has a direct correlation with the energy consumption. So we figured out that both companies are actually having similar energy performance. So this is what we also have to see. As you can see that only 1 or 2 parameters cannot answer correctly. So we need to investigate further what is the difference between two. We need to see which products they are making. So what we did was that we had data from 36 companies, for which we had the data of production quantity, yarn count, and energy consumption. We put them all in an Excel sheet, and we conducted a regression analysis. You can see this arrow where we have the mentioned baseline. There's a slope. Y is equal to 0.4476x plus 1.6506. So this is a slope value that these data is represented with. You can also do it in Excel very easily. I will show you how you do it. You plot all the data of these companies into one chart, and then you conduct a regression analysis, and you find out that there is a certain slope trend. So this line that is going from A to B is actually the slope that represents all these data points. Any factories which are above this line are consuming more energy than the slope itself. So these need to improve. All the companies who are near or on the slope are actually according to this baseline value, and those which are below the scope are actually performing even better. So this is comparing two companies, but we can use this to compare from within the company as well. So if we have this data of every month, for example, and for many years, for example, we can plot that together into a graph, and then we can see where we performed well or where we did not perform so well. it is important to first identify which are the variables that affect. As here you see in this graph, we found out that yarn count is the variable that affects energy performance. So this is an example of a weaving factory, for example, in sizing department, yarn count, width of the beam or width of the fabric, and how many number of ends do we have of this fabric. This matters. This varies energy consumption. Similarly, steam consumption in sizing varies with the same parameters as well. In weaving, for example, grams per square meter weight of the fabric and width of the fabric. These are the two parameters that impact the electricity consumption. So if the fabric weight increases, electricity consumption increases. Similarly, if the fabric width increases, the electricity consumption would also increase. In compressed air, for example, working pressure, ambient temperature, and energy promise indicator of the compressors are the variables that we need to see. Also, we need to see the relative humidity, which is not mentioned here in the example. How much humidity is going on there? So, how much air do we need to dry? So that also varies. So these are the parameters that we need to know. And then there is a parameter called environmental temperature. For example, if you see in point number 6, we have a point called ambient temperature. How do we know what was the temperature 1 year before, for example? So there is a measure called heating degree days and cooling degree days, HDD and CDD. So heating degree days are a measure of how much in degree Celsius and for how many days outside temperature was lower than our base temperature. Let's say we say that normally our operations operate ideally at 24 degrees Celsius. And if the temperature was below 24 degrees Celsius, we would say that we need to heat it more. And if the temperature is above 24 degrees Celsius, that means we need to cool down. So for that, if we need to cool down, we say it's cooling degree days. And if we need to heat up, then we say it's heating degree days. I will show you further examples. So don't get confused at the moment. I'm just explaining the concept at the moment. So degree days are based on the assumption that when the outside temperature is 24 degree in Pakistan or Vietnam, for example, we don't need heating or cooling to be comfortable in the processes. So if the temperature is above, we need to cool down. If the temperature is low, we need to heat up. So I will show you an example. Let's say the high temperature of for a particular day was 37 degrees Celsius and the low temperature was 22 degrees Celsius. The mean temperature of that day becomes 29.5 degrees Celsius. And if we subtract 24 degree from this 29.5 degree, we have for that day heat cooling degree day value of 5.5. That means we need to heat up that day for 5.5 degrees Celsius. And that is the energy we need to put in for the heating process. Similarly, if the temperature on a certain day was 13 degrees Celsius higher and lower temperature was 7 degrees Celsius, then the average temperature becomes 10 degrees Celsius. This means we need 14 degrees of heating. So this is 14 heating degree days. But the good news is that we do not need to calculate it ourselves. There is a website on which when we go, it provides us the data of the location for heating degree days and cooling degree days. So this is the website called degreedays.net. You go there and when you open it degreedays.net, you see it asks for the weather station. So in this you can write, for example, write Ho Chi Minh City. It will give you further options if you want to take general data, if you want to take data near the airport, or if you want to take data near the central city, so you can use that. And then you need to decide if you have more processes that need heating. So if it is a fabric mill, usually you need more heating than cooling. So I would suggest that you just select heating here. And in the temperature units, if you use degree Celsius or use Fahrenheit, you can use that. And base temperature, you could mention, for example, the temperature on which normally you are comfortable working on. If it is 24 or 30 or 34, whatever you think is comfortable. And then if you have the energy data divided into every day, then I think you should get a daily breakdown. But if you only have monthly data on energy, then you should also download this data on monthly as well. So it should match your energy data, whatever frequency you have. And then you can also select period covered. So with a free version, you can get data for 12 months. But if you have a paid version of this, you can even get data of 3 years or even more than that. So with the free version, we can always download 12 months data. So when we click this, we click generate data, and it automatically downloads data for the whole period, which we can then copy into our Excel sheets. So I can show you an example of such a data. You can see that in this example, we have actually downloaded the data for per month. So this data for month of January 2013, the total heating degree days is 399. So how it does is that it calculates heating degrees of every day, then it multiplies it with number of days, or it adds up heating degrees of all the days in January and gives us a total value. If we download for daily, then we would have degree days values of every day. In this example, we downloaded only for month, and this is for 3 months starting from January 2013 and finishing till June 2016. So it's a little more than 3 years, I think 2.5 or 3.5 years, I think. 3.5 years, yes. So this is the data that we have. So because the natural gas consumption was also available on monthly basis, electricity consumption was also available on monthly basis, and production was also available on monthly basis. So we compiled this data, downloaded the heating degree days data from the internet, and just copied it in front of it. And then we can easily use it for the regression purposes. And once we have this data, we need to see which of these data are correlated. So we can do a correlation in Excel. I will show you after this how to do that. It's very easy. It's not difficult. All you have to do is do some clicks, and it automatically generates the data. So if the correlation is 1, that means that these two parameters that we are correlating with each other have direct positive relationship. And then when we go from 1 to 0, you can see that these points have started to scatter. When they're scattering, this means that the correlation is reducing. So if we find out that the correlation between two parameters is less than 0.5, we normally do not take those parameters for the regression analysis or comparing them with each other. So that would mean that, let's say, if heating degree days and natural gas consumption are compared, and we find out that the correlation is less than 0.5 or near point or nearing 0, that would mean that heating degree days do not have any impact on the natural gas consumption. But if it is 0.5 or above, that would mean that it has significant impact on the natural gas consumption. Similarly, if the correlation is in negative and reaching -1, that means that they have inverse relationship. So if one parameter increases, the other should decrease. So you can see this data. To be able to use it, you first have to enable your add-ons. So if you have this tab called developer tab, you can go to the COM add-ins. If you don't have this, then you can go to file and go to options. When you are in the options, you can go to add-ins. When we click it, this is what opens. And you have to see in the bottom, we have this, it calls manage Excel add-ins. Okay. And we click go. You can see that I have different add-ins. Those which are ticked are enabled, which we have not ticked are actually disabled. So we have to enable this analysis tool pack. I suggest that you enable both tool pack as well as VBA. So you need to enable VBA if you want to automate something, but at least you can use this analysis tool pack. That is what is required. So enable it, it should be ticked. When you click OK, you come back to this Excel sheet. So now to see if it is enabled or not, we go to the data tab, and here you should see this button called data analysis. Since I am using a different version of Excel, maybe you might be using a newer version, so its location might be a little different in the new versions, but this data analysis tab is usually available in the data tab. So we click the data analysis tab, and these are different tools that we see. So one tool is correlation that we're going to use today, and another tool is regression that we're going to use today. So let's start with correlation. So click correlation and click OK. And it asks you to input the range. And we first have to see is our data grouped by columns or rows. In this case, our data is grouped by columns, not rows. And then we have labels in the first row as well. So we click this, and then we input the range. So we select all the data, the variables that we want to analyze together, and then we click. It should show us in a new sheet. We click OK, and this is the result. So you can see, for example, so this is like a matrix. So these parameters in the row and column are same, and they're compared with each other. You can always ignore these where we have same parameter in row and column. So month is compared with month, obviously the value would be 1. But we see that natural gas consumption and months have a very low correlation. It is 0.29, which is very low, which is lower than 0.5. Again, electricity consumption and month have very low correlation. Monthly production has low correlation with months, and heating degree day also has low correlation with months. But if you go forward, we can see that electricity consumption and natural gas consumption have somewhat positive correlation, but this is also not very, very significant. Monthly production and electricity consumption have a very, very big correlation. It's nearing 1. So we let's mark it green. And heating degree days and natural gas consumption also have a little bit significant. I won't call it very, very significant, but it is nearing 0.5. So we can also use this. And then electricity consumption and natural gas consumption, since these are both energy types, I think we can ignore this data because these are both are energy types. All others are not really significant. So what we need to do is now is that we know that electricity consumption is to be compared with monthly production in this case, and heating degree days and natural gas consumption are to be compared. In case of electricity consumption, heating degree days do not play an important role. It's only a matter of identifying which ones are really important. In this case of natural gas consumption, since the other parameters are also not very, very significant, we can try to use the monthly production data as well, because it is also nearing 0.4, but we can just still try it. But this also represents one important point. If the correlation is so low that it is below 0.5, this also means that there must be another significant variable which is missed. So we can always type in here that seems that another significant variable is missing for natural gas. So in this case, I would recommend that we investigate further and see if the product type is the bigger indicator, or is there another indicator that we need to keep in mind. So once this is done, now we know that for electricity consumption, we already need to do a monthly a correlation with the monthly production. So come back to the data that we had, and we again go back to data analysis. We go to regression, click OK, and this time you can see it is asking for more data than the correlation. So Y range, input Y range is the data which is dependent. So electricity consumption is a dependent variable. but monthly production is not a dependent variable. So electricity consumption is depending on monthly production, as we see. So in Y range, we select electricity consumption. And in X range, we select monthly production. And our data is labeled, has labels there. We can also check the confidence level of 95% so that our data is more significant. And then we can click OK. So this gives us the regression data. So you can see that the correlation is high. The R value is correlation, and R squared is also significant. This is representing variance, so this is also significant. We can use this data as well. So this means that when we have these values, next is that we have to look at the p value. Statistically, p value is very, very important. If it is below 0.05, then it is a significant data. So must be below 0.05 to have a significance. These are the things that we need to see. So now we know that our intercept, or we have these two values as the constant. So we have constant number 1 is this value, and constant number 2 we have in front of monthly production. So when we have the slope value now, y is equal to a plus bx. So y is our energy consumption, electricity, and x is the independent variable because we selected x in the monthly production in x. So that is monthly production, right? So if we put these two into this formula, our constant, that's A and this is B. So our value would be electricity consumption is equal to 50736.9.12 plus 526.96 multiplied by monthly production. So this would be our value of the slope. How we can use it now? So we can use it for the forecast purposes. So let's try to calculate. Let's say if we have a monthly production value of, for example, here we have a monthly production value of 179,313, and let's try to put that here. Constant A plus constant B multiplied. Let's assume that our monthly production is 200,000. That is the estimate of near future, let's say. So this is the electricity consumption that we get, the forecasted electricity consumption. We can also use it to see if we are good or if we are not so good at the moment. So we can also put this graph, this value here in front of a month. We can say, okay, our electricity consumption should be constant A plus constant B multiplied by our monthly production. This should have been our electricity consumption. You can see that in this case, so you can see that our electricity consumption was 780,000 kilowatt hours. But as per the slope value, this should have been 673,000. So we can say that we consumed how much more energy? So we consume 107,000 kilowatt hours more based on the slope. So this is how we can also identify if there were any months when we consumed more energy than we should have been. So this is how we conducted.